All right, we are rolling into section 4.8. 4.8 is continuing our study of functions and looking more at graphs and making sure that we can look at the most important aspects of the graphs and figure out general trends for the graphs when it comes to steepness, starting point, ending point, and stuff like that. So this first problem right here is talking about a flag ceremony, and they are raising flags up a certain way. The height of the flag is a function of time. Here are some graphs that are each a possible representation of the function, meaning the height at different times. It is a function because it would be passing the vertical line test, and there's not going to be any time, which is an input that would have more than one output, where the flag would be at different places. So what the students were supposed to do is look at the different graphs here, A through F, and try to explain what each one of these was saying. So on A, you can see that the flag is starting at 0, and it is going up at a constant rate, getting to its highest point at 6. We're not quite sure if that's 6 meters or 6 feet, and that would be after 5 seconds. It is a nice constant rate. No pauses, no speeding up, no slowing down, just a constant rate of change. For B, it is starting at 3 units, and it's staying at 3 units. It's not going up or down. Time is going on. It's still a function because it passes the vertical line test. No input has more than one output, but it is just going to be staying at that 3 units. The next one says that it is going up fairly quickly, starts to slow down till it stops for just a little bit. There's a pause, and then it keeps raising and gets up to 6. And now instead of like in graph A, where it took about 5 seconds, it looks like it took somewhere around 3.5 seconds to get to its full place. So we could look at that average rate of change, and the average rate of change is going to be greater than the average rate of change in A. The next one, it looks like it goes up to a 2 and then it comes back down. It goes up to 2 when it comes back down. It just keeps doing that. It never gets higher than 2, and it does this from 0 seconds all the way to 6 seconds. On E, it starts off the ground. Then it goes up and it pauses for a second, goes up, pauses for a second, goes up, pauses for a second, and just keeps doing this until it gets to its highest point, which is 6 units at about 6 seconds. Now, when we look at this, if we looked at the average rate of change, it's kind of hard to figure this out because it's starting a little bit higher, but we can compare average rate of change if we look at the beginning point and the end point and compare them to the different graphs that are on here. The next one is going up. It gets to its highest point, which is 6 units at 3 seconds. Then it instantaneously starts dropping down at about the same rate. It looks like about the same steepness, meaning the same change of height over change of time, but it is coming back down until it gets to about halfway, and it stays at halfway. The next question we had was which one of these things seemed most realistic. For me personally, I thought E was most realistic because usually when you're pulling the rope to bring the flag up, it is going to go up a little bit, and then there's going to be a pause as you reach with your other hand. So that was that. Another student who is in the Boy Scouts pointed out that E started off the ground, and that made most sense because you're never going to have an American flag or whatever the flag is sitting on the ground, especially at a flag ceremony. So it wouldn't start on the ground. I personally thought that F was the oddest and the one that didn't make much sense. It was just too perfect of the rate of change going up and then instantaneously coming down. It seems like there would be some kind of variation when you were going over and having the flag going up. Same thing with A. It's just the only way I could see that happening was if it was not a human who was doing it, but it was a robot or some kind of machine. So that was that. The next thing we looked at was problem number 2. Problem number 2 says, here's another graph that relates the time and the height. This is a relationship between time and height. Can this represent the time and the height of the flag? Explain. The answer is no. The reason why is it's saying that the flag is going to be at different heights, but the time is not changing at all. So how can it be at the different heights? The only way I could think of this is if it was just an enormous flag, and you were saying the flag was so big that it was at a height of 6 and a height of 1 unit at that 3 seconds, but still just a little strange. B says, is this a function? And the answer is no, it is not going to be a function because it does not pass the vertical line test. One input of 3 has more than one output. So no, does not pass the vertical line test. The next part here, I showed the students a video of a person who is raising a flag up into the air over a certain amount of time. and they were supposed to sketch out a graph of what this looks like. Let me pause for a second. I'll grab the graph and put it up here. So here was the person raising the flag. There was a little pause, then it went up for a little bit, then it paused, and then it went up a little bit quicker. It looked like there was a small pause right there, went to its highest point. There was a pause for a few seconds, and then it dropped really quickly. Let me pause again and bring back the So when we're looking at this graph, I felt like the flag started about 5 feet off the ground. It went up, there was a pause, it went up a tiny bit, there was a pause, it went up a little bit more. And what we kept doing here is every time something would change, I'd pause the video and we would look at what we thought about the height was and about how many seconds had passed. Before we even started doing that, we saw that the whole process happened in about 21 seconds. So the bottom, the inputs, the independent variable of seconds, I went over and went from up to 22 and we went by twos. The next one, the flagpole, looked like it was about 35 feet tall, assuming the person in there was about 5 feet tall. It seemed like there was about 7 of those people. Once we had this, as I said, there are different aspects of this. The steeper the line, it shows the faster that they are pulling the flag up. The horizontal parts are saying time is going on, but the flag height is not changing. And then you could see that it dropped down. It appeared to me that the flag height was slightly higher than when it started when she brought it back down. So that's why it ended about a little bit higher. So we can go over and look at situations and come up with a general graph. A real easy way of doing this is finding those really important points and then plotting those. On this next one, it's saying that there were 2 pools, one small one, meaning not very tall and a smaller diameter, and the other one was a bigger diameter and it was also deeper. Someone was trying to fill those up for a party. They put a hose in one and a hose in the other. I gave a little extra information. I said that the small one was 15 inches deep and the other one was 27, but I gave the additional information saying that the small pool could be filled in 4 minutes with one hose and the big pool could be filled with in 20 minutes with one hose. So we had to go over and graph these different things. The first one says that you are filling up the small pool, and then when that's done, you turn off the hose and the other one just continues to fill up. So I knew that I had a point at 0, 0. I had a point at 0, 0, and the reason it was 0, 0 is because it started empty, and then I had it at 4:15, and it was at 4:15 because I knew at 4 minutes it was completely full at 15 inches, and then it stayed flat. The next one started at 0, 0, and then it took 20 minutes to fill up. Now there is a difference in steepness, meaning the pool is being filled up at a different rate, not with water coming in, but how high the water level was. And the reason was because if you had this and you had a wide pool, you had a bigger diameter. So the same amount of water is not going to increase the water level by as much. And that is why the water level was increasing slower for the big pool than it was for the small pool. The next one states that you are filling up the pools. Once the small one is full, you stop filling the big one. So I figured out what the line would look like if it started at 0, 0 and went to 27, meaning the big pool. And then I did the small pool, knowing there at 4 minutes it got to 15 inches. And then they said that you turn off both hoses when the small one is full. So at 4 minutes, I not only turned off the small pool hose, but the big one as well. And then they both stayed at that same exact level from there on out. The last one here was each hose is in the pool and they're filling at a constant rate. So the small one at 4 minutes got to 15 inches high, and then it stayed at 15 inches high. But they said at that exact time, you took the hose out of the small one and put it in the big one. So now there's 2 different hoses going in there, which means the rate of the increase of the level of the water is going to increase more rapidly. So it's not going to take that whole 20 minutes to fill. According to my calculations, it would take about 12 minutes to fill. So it became steeper. So those were the 3 different graphs that we looked at. Now let's take a peek at the homework. The homework says the graph show the distance D traveled by 2 cars, A and B, over time. Distance is measured in miles and time is measured in hours. Which car traveled slower? Well, I said A traveled slower, and the reason why is that less distance was covered over the same amount of time. If you look at, let's say, 2 hours, car A went less miles than car B did, and the only way that's possible is that the miles per hour for B was faster than A. So that was my answer on that one. On number 2, you're supposed to match the situation with the graph. So the only funky thing you can see is BCAD. The only funky thing here is that on the graph, if you look at the description on D, it says that it is an empty 100-gallon tank. It is filled in 50 minutes. Then a dog jumps in, splashes around, letting out 7 gallons, and then the tank is refilled afterwards. Now, Mr. Olson actually is the one who pointed this out. How could it be full at that high point, splash out a little water, and then get higher than that? If with that point where I have the arrow saying that is full, it can't get any higher than that. So that was just a little odd. So number 1 made sense for B. A full 10-gallon tank is drained 30 seconds till it's halfway. Then afterwards it is refilled. That makes sense for that graph. The next one is C. A 2,000-gallon water tank starts out empty, is being filled for 5 hours slowly at first and then faster. You can see that the rate of change changes at some point. The next one is A. An empty 20-gallon tank is filled at a constant rate for 3 minutes until it is half full. Then it is emptied at a constant rate for 3 minutes. You can see it's the same rate. And then the last one was the one we already talked about, how the water was filled in, dog splashes some water out, and then it goes back up. The end of that graph looks a little weird though. The next one here, you were supposed to be figuring out which one has a greater value at 3.9. So I checked F of 3.9 and G of 3.9. The only thing I'm noticing now that I'm looking at it, the second one I said F of 3.9, it was supposed to be G of 3.9. Oopsie. So when we put in 3.9 in the first one, I got, with my calculator, 8.22. And then G of 3.9, that should be a G of 3.9, would get you 8.08, which means F of X would be bigger at 3.9. So F of 3.9 would be bigger than G of 3.9. Now on the second graph here, it is talking about a person who walks in at ground in the first level of a school. They go up 3 flights of stairs, stay there for an hour. Then they go all the way down to the basement. They stay there for an hour and then come back and have lunch at the ground level. Okay, so I'm assuming that when they say ground level, they're calling that the first floor. It's a little confusing to figure out which one is the first floor. I'm considering the first floor to be ground level, and then the second floor would be 1 up. The next one asked you to make a graph that has all this information. It says B of 0 equals 0. That is the point 0, 0, input 0, output 0. It then says that going from 1 to 7, the input of 7 should be bigger than 1. They also tell you that B of 9 equals 11. So that means an input of 9 is going to have an output of 11. It's going to be 11 high at 9. Then they tell you from 10 to 23, it should be exactly the same. So the output at 10 and 23 will be the same. And then it's saying that B of 20, an input of 20, will be smaller than B of 40, and that means it's coming down. It didn't necessarily say it came down to 0, but I put it there. And then lastly, on this one right here, let me see if I can drag this down. Drag it down, there we go. On this last one right here, it gives you a graph. It says, what are the greatest water volumes in the cooler? You can see the highest point there, the max, is going to be at 10 minutes. You are going to have a max of, it looks like about 11 liters. So you could write that as V of 10 equals 11. The next one says find the value or values of t such that V of t equals 4. The output is 4. The only time an output is 4 on this is at 2 and at like 6.1. So t of 2 and 6.1 would be V of 2 and V of 6.1 would give you that 4 of an output. Last one, identify the horizontal intercepts of the graph. What does this tell you about the situation? The horizontal intercept would be at 4, 0. That is saying at 4 minutes, there is no water in there. Hopefully that made sense. Thanks so much for watching.